So we have lab work 2. So you can choose one of these 4 tasks to perform this, to find the shortest path in the graph. You can find uh, you can find shortest paths using Dijkstra algorithm, Bellman-Ford algorithm, or Floyd-Warshall algorithm. Uh, Dijkstra algorithm is the simplest. It does not operate on negative cycles. It can operate on if the graph has negative values, it does not mean it has negative cycle. So it can operate sometimes on negative values, but if you have negative values, it's better to use Bellman-Ford or Floyd-Warshall, because if the graph is more complex or you are uncertain whether you have or not the negative cycle, so then if you use Bellman-Ford or Floyd-Warshall, then you will always be right. Now you will need to solve one of these 4 problems, just one of these 4 problems, just one problem of them, using either algorithm. But if you choose Dijkstra algorithm, it is not that difficult, so the mark will be less. Let's say you get 9. If you choose to implement Bellman-Ford or Floyd-Warshall, you will get more, you will get 10 if everything works. But if you add some additions, some additional features to Dijkstra's algorithm, let's say it becomes more advanced, or it's up to you what you can come up with. So then you can also get 10. So, and also you need to write a report. Okay, so I will a bit explain, but it's more of your task to find some additional information on the graphs, but I will explain a bit. So so Dijkstra algorithm, the simplest algorithm, it is we will implement it on this graph. So it has the visited set that now is empty, and these are the answers, the shortest path, and this is the visited set, also the answer. I keep it somewhere close. So here we start from A and we go to F. So in starting vertex, initial vertex is A, final vertex is the destination is F. Distance to A is 0 at first, because if we are standing, the distance from A to A, it is 0 because it's just distance to itself. To B, C, D, E, F, G, it is infinity at first because we don't know the distance yet. So let's say we start from vertex A and we add vertex A here because we are visiting this vertex. And from vertex A we can go to vertex B, we can go to vertex C or to vertex E. So from A to vertex B the distance is 4 because the weight of this graph, of this edge, is 4. To vertex C it is 3. To vertex E it is 7. So now from A we have to go to the shortest, to the vertex which has the shortest distance. So it is, in this case, C. In this case it is C and we write C here. We are visiting C now. We are visiting C, and from C we can go where? We can go to B, but if we add 3 plus 6, it would be 9, so the distance to B would be 9, but we already have here 4, so we leave 4 here. We don't write 9 because 4 is less than 9. From C we can go to E, but if we add 8 to 3, so then it would be 11, and we have 7. 7 is less than 11, so we leave it. Now we need to go to, sorry, I forgot D. From B, from 3 plus 6 would be 9 to B, but we leave it. Then we can go, we can in alphabetical order, we can check D. So from 3 plus 11 would be 14, and 14 would be less than infinity, so we write 14 here. Now we check what we did before, so 3 plus 8 would be 11, and 11 is more than 7, so we just keep 7 here. Now what is next? So we need to go from start to the vertex that has the lowest distance. So from A, the lowest distance would be, if we go to B here. So we mark B, as now we are in B, and B is visited. We are visiting B now currently. So from B we can go directly to D, and we just cross 14, and we write 4 plus 5, it's 9, because 9 is less than 14. Anywhere else we cannot go. Now we check which is the, we have already visited B, we have already visited C, and now the lowest distance to some of these vertices would be 7. Yes, because if we went to D, then it would be 9. So we choose 7 instead of 9 because 7 it is closer. So we go to E, and now we are visiting E. We are visiting E, and from E, and with E we can go to, from E we can go to D. 7 plus 2 would be 9, and we also have 9. So we don't upload because it's the same value. And from E we can also go to G. 7 plus 5 would be 12, and we write 12 here because it is infinity here. Maybe somehow it should be a little bit nicer. So 12 here. Maybe a bit nicer. So 12 here. And now we were visiting E. So now we need, the visited vertices are A, C, B, and E. Now we need to go to the vertex that has the lowest distance. So the lowest distance we can choose from 9 and 12 so far. So the lowest distance would be we go through this path to 9, or we can also choose this path to go from here, just because it's also 9 as we remember. Yeah, so now we are visiting D. We are visiting D, and from D we can go where? We can go to F, so 9 plus 2 would be 11, and we write this 11 here. From D we can go to G, but 9 plus 10 would be 19, and 12 is less than 19. So now we are visiting, so we don't write it here 19, so we leave it 12. So from D, then we can go where? We can go to the lowest, the vertex that has the lowest distance, so it would be F. So and here we can see that we have finished our journey, and we just found the shortest path. Just for completion, we can from F we can say that we have 11 plus 3 would be 14. 14 is more than 12, so we just leave it and just don't go anywhere. Also, we can visit, I marked here G is not necessary, but also from F we can go to G and at G. So from G we can go to, we probably don't have anywhere to go, so just we can recalculate the pathways that from G to 12 plus 5 would be 19, which is more. From it would be 12 plus 10, it would be 22, what is more to D. So from G to F would be 15. So this G is just additional. We can in the end check whether there is the shorter path or something, but now we found the shortest path to F, and that is okay. So what are the paths here? You can see that from A this path goes to C, but it stops here, so this is not a path. So the path would be A, B, D, F. You see we have this path going like this, and also there's a path A, E, D, F. So A, B, D, F or A, E, D, F. So this Dijkstra algorithm helps you find the shortest paths. That's the simple graph. Now this is the pseudocode. So you can go deeper in details by yourself. So so basic things what I hear. So distance to the source vertex, initial vertex S, it is 0 as we marked. So for all vertices that are V is the set of vertices, so minus initial vertex. So for all vertices that are other vertices than initial, so distance is marked infinity. The set of visited S is the set of visited vertices. It is initially empty. Then all the vertices are in the Q. Q is the set of vertices that will be checked, will be evaluated for distance, for the lowest distance. and until the queue is empty, the operation is the operation to find minimal distance is performed, and this means the so for all the this means the how is this called, maybe the conjunction or unification of set S and U and vertex U. So S and U the vertex U and from all the set they are added to visited vertices. So U is added to list of visited vertices. So for all V that are neighbors of U, so they are searching for the shortest path. So if you have, let's say, distance to U 5, and the distance from U to V, it is, let's say, 3, while the distance to V, it is 9. So so it means that in this case you found the shorter distance, and this shorter distance is now added to as the new shortest path, as the new value of the shortest path for the vertex V. So it means that you, by checking, let's say, you may go to here, but here you would have 3 plus 11 plus 2 would be 14, 16, but by going here you get 11. So then by checking, by adding these vertices one to another, you can find the shorter path, and just this is written in for each vertex in detail. So you, for all the vertices, yeah. So one by one he's checking the here, and it sees that it found the shortest path through here. Yes. So this is the search for the new shorter path. So Dijkstra algorithm. So now we go to Bellman-Ford algorithm. Bellman-Ford algorithm, it can find, it can work with negative values. When there are negative values, they can be negative cycles. Not always, but sometimes in some cases. So if we have negative values, it's better to use Bellman-Ford or Floyd-Warshall. So Bellman-Ford algorithm, it's performed by iterations. So by, let's say, the set of steps. So if you have 1, 2, 3, 4, 5, 6 vertices, so there would be 6 minus 1, it means 5 iterations. So not usually all those iterations are necessary, because at the last iterations there may not be any changes. So how this is performed, I wrote here the iterations. So basically it is the similar thing. We write this S, it is the initial vertex. So we start from S. And we just looking for the shortest paths to all these vertices. So in this case, in this example, we're looking for the shortest path to all of these vertices from this initial vertex S. So from S to S, the initial distance is 0. To all the others, it is infinity, like in Dijkstra. Now what we do, so from S, while visiting S, we can go where? We can go to A with the distance 10. So we write here 10. And from S we can go to distance to E by 8. By 8. To E by 8. So from S we can't go anywhere. From A we can go where? From A we can go to C by distance 2. From A we can go to C by distance 2, but the distance to A was 10, as you see, 10. Yes, we wrote here 10 and here the distance 10, so 2. So to C it is 12. So it is 12. Now, so from A we can't go anywhere else. So from B, when we are visiting B, so we from B we can go to A by 1, but we don't know how to go to B yet. So we don't know what is the distance to B, so it would be infinity plus 1, and we cannot write here anything yet. So we leave it. So we go to C. To C we know how to go to C because the distance is 12. We go from S to A, at A 10, to C plus 2 it is 12. So from C we can go to B with the cost of minus 2. So 12 minus 2 would be 10 here. And now from C we just can go to B, what we wrote here. So from D, now from D what we can do, from D we can go to C or we can go to A. But we don't know how to reach D yet. Now from E we can go to by 8 to, from E we can go here to D. From E to D it's 1, and from S to E it's 8. So 8 plus 1 would be 9, and we can go to D by 9. Yeah, so this is the first iteration. The first iteration. So here you can find all these iterations because they just didn't fit to the space, so they are somewhere here. If you minimize this, you will see the iterations, because if I minimize, these will disappear. So I won't minimize. So now this was the iteration number 1. Now we can continue. From S we can go where? From S we can go to A by 10, and from E to E by 8. So it is the same. From A we can go where? To C by 2, so it will be 12, the same. From B we can go to A by 1, so from to B it's 10, and by 1 plus 1 it would be 11. To A it would be more, so we don't write it here because we have 10 that is less than 11. From C we can go to B, it is the same, 12 minus 2, it would be 10, and B has 10. Now from D we can go where? We can go to A. Yes, by minus 4, so 9 minus 4 would be 5. So here we write 5. Here we write 5 from D. And also from D we can go to C by -1. So D -1 to C would be 8 at C. This was from D, yes. Now from E we can go to D. From E we can go to D by 1 and it's the same line. So I will write here the same values. So we completed the iteration number 2. Sorry, what's happening here? My pointer does not work well, so it's 10, 8, this is 9, and this is 8. So this is iteration number 2 and this is 0. Now, what we have now, from S, this it is the same. From S we go to these two. From A has 5, so from A we can go to C by 7. From B we can go to A by 1 and this would be 11 and A already has 5. From C we can go to B. C has now 7, 7 minus 2 would be 5. From D we can go where? We can go to A, minus 4 it would be 5, the same, C, 8, the same. So we just finished iteration number 3 and we just write all the other values the same. Now iteration number 4, to S it is the same, to A. From A we can go where? We can go to C by 7 and we have 7. From B we can go to A by 1, so B is 5. If we add plus 1 would be 6, well, we already have 5 so we don't need 6. From C we have 7, at C we have 7, so from C we can go to B. 7 minus 2 would be 5, what we already have. From D, at D we have 9, so 9 minus 4 would be 5 for A, so we already have this. From D we can also go to C, so 9 minus 1 would be 8 for C, but we already have 7. From E we can go to D, so 8 minus 1 and it would be from E we can go to D, so E plus 1 and we can go to D, we have 9, we already have 9 here. So for the fourth iteration it would be the same numbers that would be. So you can see that nothing changes. And it would be the same for the fifth iteration. So you can see that from some particular time that nothing changes. Now we just try to show you the 5, 5, 7, 9, 8. You see the same is here. And all the numbers should be the same. 10, 10, 12, 9, 10, 10, 12, 8, 5, 10, 8, 9, 9, 8, 5, 5, 7, 8, 9, and 5, 5, 7, 8, 9. So the same thing as it is given here, yes? You will all have this in video. Now there are some hidden slides with algorithms that I use for myself, but I don't want, just don't need to show this for you right now, because that's not very important. So let's go on now. Pseudocode for Bellman-Ford. So Bellman-Ford is, again, it is graph. It is given that it's graph G with initial vertex S. V is the set of vertices. Distances are marked infinity, so distance S is 0, so everything is the same as for Dijkstra. Now it is checking for the distances. For the shortest distance is the same as Dijkstra, and it's adding those shortest distances. But it also can find negative cycles, and it can show where the negative cycles are. But what's more important, it doesn't get stuck with the negative cycles. So I will leave to clear out these things for yourself a bit more, because it is directly connected to your task to gain deeper understanding. So I just tell you some basic things. So here, the detection of negative cycles. Here it is a bit tricky. So these are algebraic equations from algebra simple. That it's saying that maybe it's difficult for you to understand right now that distance from distance A, it is distance B minus 9. Distance B minus 9 is distance A, yes. Distance B, it is distance C plus 3, yes, it's okay. Distance C, it is distance A plus 4, distance A plus 4 is distance C. So this is all correct. Then the mathematicians tend to add all these columns, like columns, this column, this column, this column right here, this column right here, and this column right here. So they get that 0, it is less or equal than -2, and they get the contradiction. This means that there exists this inequality, let's say. What is here? So here, if we have this, if this is true, then somewhere there is a negative cycle. So distance A, it is what? It is -9. So this is the same equation, dv more du v uv. It is the same equation as given here, dv du v uv, yes. And now distance, let's say v, if we just starting from B, so we are just starting from B now, and let's say distance, and we were checking each vertices. So distance A, distance A, it is from B to A, it would be -9. From B to B, it would be 0. From B to A, it would be -9. So if we just add them together, we see that in this case it is equal. So -9 is equal to -9. So in this case it is equal. so this inequality is not correct. So because in this case it is equal, yes, minus 9 is equal to minus 9. Now here distance B, it is also 0. Distance C is minus 5. So minus, if we start from B, minus 9 plus 4 would be minus 5, yes. Now weight CB, so from C to B, it would be 3. So minus 5 plus 3, so it means minus 2. And 0 is more than minus 2. This means that this inequality is correct. Here, so this means that we have a negative cycle associated with C. Although the if we go back to this, so we see that the negative cycle is associated with parent. So parent V would be U. So in this case we have V here, it is B. So parent of B would be C. So parent of V, it is U. So here we have B and here we have C. Yeah, B and C. So parent of B would be C. So it means that there is a negative cycle associated with C, although the negative value is here, associated with AB, yes? So this is a bit tricky that it is associated with C. So if we do calculations for A, do calculations for B, everything is okay. But if we do calculations for C, then we get negative cycle. So this is where the negative cycle is. So that I wanted to explain is that that the negative cycle, it does not mean that if you have negative value, will have negative cycle. If you have negative value, but you are calculating the distance for C, then you will get a negative cycle. And here it is, everything is okay for C. This inequality is incorrect because you get minus 9 plus 4, it will be minus 5, and minus 5 it is equal to minus 5. So this is not correct. So in this case it is equal. So in this case where it is correct, there we have a negative cycle. But I just wanted to show you that the negative cycle, it is not always associated with these two vertices, but it's more associated with this vertex, because when we are calculating the distance for C, as starting from B, yes, we start from B and go to C. So distance B is 0, distance to C it is minus 9 plus 4, it would be minus 5, and the distance from C to B, it would be 3. So when we are starting from B and calculating the distance for C, then we get a negative cycle. Yes, we're calculating here the distance for C. This is 0. This distance for C, it is minus 9, 4, and this is minus 5. And weight CB, it is, we're going back to another other side. So that's where going back from this other side, it creates that negative cycle here. Try to think here a bit, to just go to put it in your minds, and you will see. So although here we have negative value, but when we calculate for distance for C, because this negative value also goes to the distance for C, because we're going in this direction, because the graph is is orientated graph, directed graph. So this is what I wanted to tell you. So basically what you have to do, it is this, choose one of these, apply Dijkstra, Bellman-Ford, or Floyd-Warshall. Floyd-Warshall I didn't discuss. I will leave it to you. If somebody, it's more difficult algorithm, is if somebody is able or think that they are able to do it, it would be very nice for you to choose it and to just to clear out by yourselves. So it would be just additional work for you. So if you want higher marks, so choose Dijkstra and add something, some additional lines of the code, so to improve that Dijkstra algorithm in some ways. Usually students are very creative, so they find some lines to improve. You can choose Bellman-Ford with negative weights. For higher marks, and you can also use Floyd-Warshall for just if you successfully perform Floyd-Warshall, it would be work by yourselves, and it would be high mark by all means. So this is it. Thank you for listening, and we will meet next time. So as you know, I'm not that, as I wrote you, I'm not that strict with the scheduled dates that we agreed for defending. So you can postpone the defending by 1-2 weeks, but just don't come in the end of the the subject in May, before the exam sessions with all the lab works, because then it would be a lot of things for you to do and to just and to defend, I mean, all the other subjects. So just postpone, but not too much. So good luck, and see you next time.